The first thing that you have to make yourself familiar with when you start learning data structures and algorithm is big O notation. I have not seen any programming interview where they don't ask about big O notation, data structures and algorithm. In this video, I am going to tell you what is big O notation by using few simple examples. Big O notation is used to measure how running time or space requirements for your program grows as the input size grows. In this video, we are only talking about running time. Let's say you have this function foo which takes an array or a list as an input and it does some processing and it returns some output. When the size of array is 100, it runs in 0.22 millisecond. When it's 1000, it takes 2.3 milliseconds. So as the size grows, the time also grows. And let's say this is the graph of size versus time. You can clearly see that it's a linear function. The time that it takes to run this program is linearly proportional to the array size, and any linear function can be represented as a cross n plus b. Now the reason we are using a mathematical function here to measure the time requirement is because depending upon the computer, this time might be different. I have a fast computer, so let's say it's 2.3 millisecond, but if you have a slow computer, it might even take 5 milliseconds. So measuring time of the program in absolute terms is not useful. It has to be mathematically represented, and that mathematical representation is big O. Here we are not going to say the time is a big O of a cross n plus b, but we are going to apply some rules. So the first rule is we are only going to keep the fastest growing term. The b here is constant. So as the size of n grows, let's say n is 100 and a is 2, right? So it will be 200. But when n becomes million, when you multiply by 2, it becomes like 2 million versus b remains constant. So the fastest growing term is a cross n. So we only keep that. The second rule is we drop any constants. So constant is a and we drop it. So what is left is n. And now we say the big O time complexity for this program is order of n. This is the example of a program whose time complexity is order of n. Let's say you are squaring the numbers by taking an input list. So this is the Python program. Now let me clarify, this big O notation is used for all programming languages. It is not specific to Python. I'm just using Python as an example here. In this example, you are running n iterations. So right now my array size is 4, so it did 4 iteration, but let's say if my array size is 4 million, it's gonna do 4 million iterations. And as you know, the time that it takes to execute the program is equally proportional to number of computation it is doing. Here, if the size is 4 million, it is gonna do 4 million computation in this for loop. Hence the time will grow linearly. Therefore, the time complexity for this program is order of n. This is another example where when you increase the size of an input, the time is almost constant. It changes but only a little bit. So you see like 0.22 and 0.23 millisecond. So the graphical representation of the time as the input grows could be this, and it's a constant function, and constant function can be represented by time equal to a, where a is the constant. And when you apply those two rules, what you get is order of 1 complexity, because the way you can look at a is a cross 1, and then by second rule you can drop that constant which is a, and what you get is order of 1. This is the example of a function whose complexity is order of 1. Let's say you are trying to find the PE of the first stock in your list. So here I am getting the stock price in a list. I'm getting EPS of different stocks in the list. So these two lists have price and EPS for different stocks. There could be 10 stocks or a million stock. But when you supply an index, it is going to do a constant operation. So it doesn't matter what is the size of price or EPS. It could be 10, it could be a million. The time execution is going to remain constant. Hence, the big O complexity of this program is order of 1. This is another program where you're trying to find a duplicate from your list. Here we are running 2 for loops, and you're comparing the numbers in two for loops and trying to find a duplicate. You might be aware about this program. The linear equation for the timing of this function as the list grows is a cross n square plus b. This is the standard linear equation, okay? And here when you keep only the fastest growing term, which is a n square, and drop the constants such as b and a, you will get order of n square. Here is another example where in this program the first block of code is doing n square iteration, the second block is doing n iteration. So to represent the time, you can use this equation, a n square plus b n plus c. But in this equation, again apply those two rules. Keep the fastest growing term, which is a n square, drop bn plus c, and then also drop the constant, which is a, and then you get order of n square complexity. So sometimes people say the complexity of this program is order of n square plus n, but no, it is order of n square. And I will explain you why you apply those two rules. Why do you keep only the fastest growing term? So let's understand that, the reasoning behind these two rules. Let's say you have a function which is something like this, 5n square plus 3n plus 20. Now big O is a very rough ballpark estimate. It refers to the value of n, which is very large. I'm not going for any large value here, but let's say even if n value is 1000, in that case, in this equation, the first term will contribute the most. It will be 5 million, whereas the second and third term will come around 3020. Okay, so 3020 is very minor against 5 million value, hence it can be dropped. Big O is a simplistic method of saying this is how much my program is going to take. Hence it makes sense that you only keep the fastest growing term and drop everything else. Until now, whatever we saw was for running time growth. It is called time complexity, but the same can be used to measure the space growth, and that is called space complexity. Let's look at one more example of binary search. When you have a sorted list of numbers, if you want to search for a specific number, how do you do that? In this example, I have 8 numbers. I want to search for 68. Simple method is you go through all the numbers one by one and compare again 68 and find the index. This has order of n complexity. This is a very simple example, so this program will run fast. But let's say you have billion numbers in your list and you want to find out the index of a specific number. You don't want to do billion iteration because it might be very time consuming. There is a better way, which is binary search. In this, what you do is you first find the middle element, which is 21. You compare it against 68. You find out that 21 is less than 68. Hence, you now discard the array on the left hand side. So number 4 to 21, you discard it. And now what you have is 34 to 91. In that array also, you find the middle element. So you basically in each iteration, you are dividing the array by 2. Here the middle element is 57. Again, compare it with 68. 57 is less than 68. Hence you discard the left hand side array, which is 34 and 57. You now have only 68 and 91 in your search space. Again, you divide it by 2. You take the middle element, which is 68, and 68 is the element you were looking for. So you found your answer in 3 iterations. If we had done n iteration, which is the previous approach, we would have taken 7th iteration because the element is the 7th number. Okay, so this is better. If you have big array and if you are doing like k iteration, equation on the right hand side shows that for iteration k, you have to do n divided by 2 raised to k operation for k iteration. Now let's convert this into big O. So we have to do n divided by 2 raised to k iterations to get the array size to 1. 1 because that is our worst case estimate, okay? You might find your answer in, let's say, first iteration itself if the element you are looking for is exactly in the middle. But big O notation is used generally to measure performance in worst case scenario. So we always talk about worst case scenario when we are thinking about big O notation. Here, to reduce the array size to 1, you have to do n divided by 2 raised to k iteration, and that you can represent in this equation. So here 2 raised to k you can take here, and it becomes n is equal to 2 raised to k. After that, you can apply log to the base 2 on both sides of your equation. You get this. Now you know that this right hand side equation you can represent as k into log 2 base 2. Now log n base n is 1, so this part becomes 1. Hence my k, which is number of iteration that I need, is log n. Hence the complexity of binary search is order of log n. Here I had 8 elements, so for 8 elements I can apply order of log n equation, and it will be 8, you know, it's 2 raised to 3, 3 comes ahead, and log 2 to the base 2 becomes 1. Hence you find the answer that this is 3 iteration. When you go to programming interview, often they will ask you a question, and let's say for this binary search problem, let's say you did order of n iteration, which was our first primitive approach. The interviewer will ask you, can you do the same thing with a better performance? Or they can say, oh, this order of n looks too slow, can you do it in log n? Okay, so now during the interview you need to have the clear understanding of what log n means versus what order of n or order of n square means. That's all I had. Thank you very much for watching. If you have any question, please post a comment below. I try to answer as many comments as possible. Also, data structures and algorithms are very important, especially in programming interviews, in the interviews of data scientists as well. So it's important you get these concepts clear. Without a good understanding of data structures and algorithms, one cannot become a good programmer. It's just not possible. So data structures and algorithms are crucial no matter what programming languages you are using. I'm going to do a complete data structure series after this video, so please stay tuned.